Good morning and welcome you all to this session on the course on fluid machines. Last class we discussed the power developed by a Pelton wheel and how the hydraulic efficiency and the overall efficiency are defined, and the condition for which we have the blade efficiency or the wheel efficiency maximum, and also the practical condition for which the overall efficiency is maximum. Now, today we will start the discussion with one thing, that this bucket, if we go back to our earlier picture of a basic wheel of a main wheel of a Pelton turbine or Pelton wheel. Now, the shape is a spoon shaped bucket, which already we discussed earlier. Now, we did not discuss this in the last class about these angles of this blade or the bucket at the inlet and outlet. Now, it was told that inlet, the angle is in the direction of the tangential motion. That means, if we define the angle with respect to tangential directions as beta 1 and beta 2, that is the blade angle at inlet and outlet, angle made with the direction of motion, that is tangential direction. Now, at inlet, the blade is made like this or the bucket is made like this, the cross section of the bucket, that beta 1 is 0. This we already realized and we use this. The velocity triangle becomes a, or the velocity vector diagram becomes a straight line. Now, this is the outlet velocity triangle or the velocity vector diagram, where we have denoted beta 2 as this angle. This is beta 2 or theta 180 degree minus beta 2 as the angle of the bucket at the outlet. Now, from the momentum change point of view, for the maximum change in the angular momentum, that this VW2 should be maximum when beta 2 is 0, should be maximum, and in that case beta 2 will be 0, which means that the velocity of the fluid relative to the bucket has to be deflected by 180 degree, completely opposite to its inlet velocity or the velocity at inlet with respect to the bucket. To do that, beta 2 has to be 0. From here also we see that beta 2 0, we get the maximum value of BW2, and hence in the maximum change in the angular momentum and hence in the maximum driving torque or the maximum energy transfer to the wheel. But though it is true from theoretical point of view, it cannot be realized in practice, because if we make beta 2 0 and make this velocity relative to the bucket, that means this relative velocity VR2 just opposite to that of V1 or VR1, then what will happen? The jet coming out of one bucket will hit the preceding bucket, will hit the back of the preceding bucket, which may cause damage to the buckets. For these reasons, the 180 degree angle is not made for theta, and theta is made equal to 165 degree, and hence beta 2 is 15 degree. So, this is the recommended blade angle at outlet, where the recommended blade angle at inlet is 0. So, therefore, we can write here 15 degree. That means, this corresponds to theta, if you define theta this way, 165 degree. Now, next we are going to derive an expression of specific speed for a Pelton wheel, specific speed for a Pelton wheel. Now, if you recall, the specific speed is defined as, for a turbine, NST is defined as N P to the power half H to the power 5 by 4, N P to the power half H to the power 5 by 4. Now, for Pelton wheel we can write this P. What is this P? N is the rotational speed of the turbine, P is the power developed by the turbine, H is the head available to the machine, to the turbine. Now, if we define this power developed in terms of an hydraulic efficiency this way, that rho Q dot is the, rho is the density, volume flow rate, into GH, where H is the head available at the inlet to the machines, times the hydraulic efficiency. That means, this is the definition of hydraulic efficiency, P divided by the energy, rate of energy available at the inlet to the machine, rho Q dot GH, where H is the gross head. If we define in this fashion eta H, and at the same time if we use this relationship, Q is equal to pi d square by 4, and at the same time the inlet jet velocity to the wheel V1 square, or rather first I write V1 is CV root over 2 GH, that is from the use of Bernoulli's equation, where we get V1 is root over 2 GH and multiplied by a factor CV known as coefficient of velocity, which takes care of the friction in the nozzle. So, if we define this way, then we can write this thing as P is equal to rho pi, okay, rho pi. Now, we take eta H here, take these things together, pi d square by 4. So, d square by 4 into V1, okay, pi d square by 4 into V1, and again GH is V1 square by 2 CV square. So, combining these two, we can write 4 into 2, that is it will be 8 CV square V1 cube, CV square V1 cube. That means, we are substituting Q as pi d square by 4 rho, this is eta H. So, d square into GH, Q is equal to pi d square 4 into V1, sorry, pi d square by 4 into V1, I am sorry. So, V1 and GH we can write V1 square by 2 CV square. So, V1 cube by 8 CV square. This is P. Now, if with this value of P and the rotational speed n equals to u by pi d, if n is the rotational speed in revolution per second RPS, and if u is the meter per second the linear velocity, and d is the diameter in meter, we can write n is equal to u by pi d. Now, if we replace this in the equation, what we will get? We will get NST is equal to u by pi d. First we write n u by pi d, that is n, then p to the power half, that means rho to the power half, pi to the power half, eta h to the power half, d V1 to the power 3 by 2, then this will be 8 to the power half, and this will be CV. Then h to the power 5 by 4, this is the numerator, n p to the power half for the specific speed. The denominator h to the power 5 by 4, we replace h in terms of V1 again. GH is V1 square by 2 CV. So, h is V1 square by 2 CV, 2 G CV. So, just it is in the denominator. So, therefore, we can write, just you watch or you see, CV square 2 G CV square 1 by h divided by V1 square, V1 square. It is 1 by h whole to the power 5 by 4. Okay. So, this can be written in this fashion. Now, if I take all these constant together, that means it is like this. If we take g to the power 5 by 4, then pi to the power half, pi to the power half, this pi to the power half, then rho to the power half, eta h to the power half, eta h to the power half. Okay. Then CV, before coming to, okay, let us see CV is 5 by 2 and here CV is 1. So, 5 by 2 minus 1, the CV to the power 3 by 2. Now, 8 to the power half and 2 to the power 5 by 4. It is 2 to the power 3, 3 by 2 minus 5 by 4. It will be 2 to the power 1 by 4. 3 by 2 minus 5 by 4, 1 by 4. So, G has come here, CV we have taken, eta h rho pi, then left, what is left? The left part is u by V1. How V1 comes? V1 is 5 by 4, V1 square 10 to V1 to the power 5 by 2. Okay? And here V1 to the power 3 by 2. That means there will be only V1 at the denominator, u by V1, and this D and this D will make it d by d. So, therefore, the specific speed of the Pelton wheel can be expressed by this formula, g to the power 5 by 4, the formula remains like this, rho to the power half, the hydraulic efficiency eta h half, Cb the coefficient of velocity 3 by 2, pi to the power half 2 to the power 154 into u by V1 d by d, which clearly tells that the specific speed depends mainly on these two non-dimensional parameters, the ratio of bucket speed to the inlet jet speed, bucket velocity to inlet jet velocity, and the ratio of the jet diameter to wheel diameter. Now, these values are almost constant. Now, G is local gravity. If we take the usual value of rho for water and eta h usually lies between 0.85 to 9, 0.85 if we take the typical value. The typical value of CV equals to 0.97. If we take the usual values happen in the practice, this eta h and CV, and at the same time we know that if we think that this wheel will run at its maximum efficiency, maximum overall efficiency, then u by v is roughly equal to 0.46. So, these values are almost fixed, these values are fixed rigidly, and this value is almost fixed, it runs somewhere at this value 0.46. So, if we use this value, then we can express the specific speed of the Pelton wheel by putting these values. You get this type of expression with 105, which is a dimensional constant, because this has an unit, that unit is kg, as I have already told, second to the power minus 5 by 2 meter to the power minus 1/4. So, in this unit. So, this is a dimensional unit. This shows that under usual conditions, a Pelton wheel specific speed is a function of d by d, that the ratio of jet diameter to the wheel diameter. It can be expressed in this fashion, that this is inversely proportional to the ratio of wheel diameter to jet diameter. This is one very important information. Now, Pelton wheel is usually very efficient at a small head, so that small available head, usually specific speed lies between 5 to 20. That means, the specific speed of a Pelton wheel usually lies between 5 to 20. Of course, this depends upon the number of jets. With a smaller number of jets, this value is between 5 to 20. And if you take this value from 5 to 20, the value of d by d becomes equal to, from this expression, is 105 by 5 or by 20. That means, this something like 6 to 25, roughly 5 or 6 to 25. This is the value of d by d. So, therefore, you see the ratio of the wheel diameter to the jet diameter depends, the range of these values depends upon the range of the specific speeds. Now, there are certain things to be known at this stage, that if we have a large d by d, what will happen? If we have a large wheel to jet diameter, then the machine will be large and the speed will fall. It will have a lower speed, but the machine will be large, for which the mechanical efficiency will also be low, which is not desirable. Similarly, if we have a small d by d, then what will happen? For a small d by d means small wheel diameter, then to get a given power, we have to give more number of buckets, so that the bucket spacing are closer, for which the hydraulic efficiency falls drastically, and that is also not desirable. So, from these 2 points of view, that means 2 contradicting points of view, a optimum value of d by d, optimum value of d by d is lies between 14 and 16. So, that it should not be very large to machine making unnecessary large, bulky, slow running, and ultimately leads to a low mechanical efficiency and overall efficiency, and again not to be very small to have more number of buckets with close spacing, also to have a lower efficiency. So, a compromise between the two will be made, and usually the Pelton wheel gives high efficiency with a lower head. So, that we tell that Pelton wheel head is low means what? Sorry, at a higher head, I am extremely sorry, at a higher head, when head available is high, that means the specific speed is small. I have told the usual specific speed range is 5 to 20 in this unit. That means, at these values of specific speeds, these low values of specific speeds as compared to other machines, the Pelton wheel runs at high efficiency. That means, Pelton wheel is suitable for low specific speed, means at a high head, where the head available is high. Okay. After this, we will come to a very important phenomena, what is known as governing of Pelton wheel. And in fact, the governing of Pelton wheel, the principle is same as the governing of any turbine. So, first of all, you have to know what is meant by governing of any turbine. So, that the governing of any turbine, if you know the basic principle is same, which is utilized in different way in practice for different turbines, Pelton wheel or reaction turbine. So, what is meant by governing of turbines? Now, as we know, the turbines generates the mechanical power, which is converted to useful electrical power by the use of an electrical generator and alternator, which is coupled to the turbine. Now, to maintain a constancy in the frequency of electrical power output, the rotor of the turbine has to rotate with a fixed speed. So, therefore, the constancy in the rotational speed of the rotor has to be maintained. Again, from another viewpoint or from another side, you can see the speed of the rotor of a turbine depends upon the driving torque, which is given by the fluid flowing through the blade passages by its change of angular momentum, and the resisting torque, a balance between the driving torque and the resisting torque, and this resisting torque comes from the electrical load. So, a balance between these two torque helps the rotor or enables the rotor to run at a constant angular speed. Now, what happens when this electrical load changes because of the demand, either it falls down or it goes up, then what happens? The speed of the rotor of the turbine changes if we do not change the driving torque. If we do not have any mechanism to change the driving torque, so speed of the rotor will change, the rotational speed will change, which is not desirable, because the frequency of the electrical output will change. Now, how to restore the initial speed? This can be restored by manipulating or changing the driving torque to the desired value of the resisting torque because of this change in load. Now, for example, if the load is decreased, then what happens for a given driving torque? The speed of the rotor will increase. So, therefore, we have to reduce the driving torque. Similarly, if the load is increased, then what happens for a given driving torque? That means the resisting torque is more, the speed of the rotor falls down. So, therefore, we have to increase the driving torque to boost up the speed of the rotor, rotating speed of the rotor to the earlier value. And this change or control in the driving torque is done by change in the flow of fluid, because the energy that is given to the turbine rotor is directly proportional to the fluid flow rate. So, therefore, by changing the fluid flow rate, it is done that when the load is reduced, we increase the fluid flow rate to increase the driving torque. When the load is increased, we reduce the fluid flow rate to reduce the driving torque, to make a balance with the resisting torque that changes because of the change in the load, to maintain the constancy in the speed of the rotor and hence in the frequency of the electrical power output. This is in simple the basic idea or genesis of governing of all turbines. Now, this is done in a Pelton wheel. How? Now, Pelton wheel has a added constraint, because we know that Pelton wheel runs at maximum efficiency for a desired value of u by V1. U is the rotor speed and V1 is the jet speed. So, if you reduce the fuel flow rate, then V1 will be reduced. Okay. Now, when V1 will be reduced, then u by V will be changed. V1 will u by V1, for example, increased. So, we have to see that the change in V1 is not desirable, because this will change the ratio u by V and the machine will not run at its maximum efficiency. You understand that to keep u constant, if you change V1, then u by V1 ratio will change. Why the question of changing V1 comes? Because you have to manipulate with the fluid flow rate. Fluid flow rate is increased or decreased. If you make a decrease or increase, then V1 usually gets increased or decreased. So, therefore, for a Pelton wheel, the attention has to be made that the change in the fluid flow to the turbine should be done in a way that V1 remains substantially the same. Since for given U1 or given U, there is a V1 for the machine to run at the maximum efficiency. For example, for maximum overall efficiency, it is 0.46. So, therefore, U by V1 is 0.46. So, V1 has to be U divided by 0.47. U is kept same. So, V1 has to be kept same. So, the fluid flow rate has to be changed, not changing the flow velocity. How it is done? It is done by changing the area in such a way that the flow rate changes along in same proportion with that of the area by keeping the fluid velocity same. And this is done in a Pelton wheel by the use of a spear valve. So, you see this is a spear valve. This is a spear valve. Now, this is the nozzle. So, by use of a spear valve in a nozzle. Now, what happens with the load, the spear valve, the entire spear, the moves in the nozzle in this direction. So, what happens when it moves in this direction? It controls the annular flow area. This is the flow area, the annular flow area. It is increased or decreased depending upon the motion. If it moves in this direction, this area is decreased. If it moves in this direction, the area is increased. And accordingly, what happens? The change in area changes the diameter of the jet. The flow takes place, the streamline is such that it again meets and changes the diameter. Diameter is reduced or increased. Here it is increased or it is reduced. That means the cross sectional area of the jet is changed in such a way that the change in the mass flow rate of the fluid as demanded by the change in the load should be in proportion to the change in the area, or other way the change in the area should be in proportion to that, so that we can implement or we can execute this change by keeping the velocity same, because velocity V1 is equal to Q dot rho, that is mass flow rate, divided by the cross sectional area of the jet. cross sectional area. So, what is happening is that these two are changing by keeping the V1. When this is reduced, Q is reduced, keeping the V1 same. This is increased, Q is increased by keeping the V1 same. This is done in this situation to maintain V1 same. Now, this is a case where low load, the area is reduced and the jet area is reduced. The annular area is reduced, jet area is reduced, so that it gives less flow rate. And this is a situation where this is for high load, that means the jet area is relatively high. Now, in certain situation, if there is a sudden decrease in the flow rate, then what will happen? You have to suddenly choke the flow like this. That means you have to keep the sphere like this. Choke means this stop the flow. Don't confuse it with the choking of the compressible flow. That means you have to stop the flow like this. So, sphere have to move suddenly to this section, to this part, the downstream of the nozzle. That may create a problem of water hammer. That means a pressure wave may be generated which may go to the upstream and cause the problem of water hammer. So, to reduce that problem, what is done? A deflector plates are used which deflects the water from the main stream for the jet to reach the Pelton wheel, so that the sphere movement may be done slowly. That means, the deflector plates help in reducing the flow rate along with that done by the sphere movement, so that the sphere movement in the nozzle may be slow and the water hammer problem may be reduced. So, that the deflector are used to deflect the jet from the bucket for reaching to the Pelton wheel in case of a sudden decrease in the load. So, this is all about the Pelton wheel, but before I close this thing, I tell the limitation of the Pelton wheel. So, after reading that, one can understand the Pelton wheel works well at a relatively higher head or a lower specific speed, because it has to compromise with the ratio of the diameter of the wheel and the jet diameter to have a wide range of specific speed for its efficient operation, or to operate at a relatively lower rate or a higher specific speed. This we have discussed. Otherwise, what will happen? The efficiency, the mechanical efficiency will reduce, the hydraulic efficiency will reduce. So, we cannot have efficient Pelton wheel at this lower head or higher specific speed. So, for these reasons, the Pelton wheel cannot be used for those purposes, and a solution to that is given by another class of turbines, reaction turbines, which we will discuss in the next class. Okay, thank you.